we were designing op-amps, and we saw a way of realizing higher DC gain without changing too much. That's by adding cascode devices to both the input pair and the current mirror. And the way we chose to implement it was to the NMOS differential pair, we added NMOS cascode, NMOS common gate devices, and to the PMOS current mirror, we added PMOS common gate devices. The result was something that looks like the simple op-amp, but with two more set of transistors stacked. The role of M1, M2, M3, M4 are exactly the same as before. Okay. And M5 and M6 are common gate devices for the input pair, M7 and M8 for the current mirror. Okay. So this, of course, it's understood that the gate bias for M0 comes from a current mirror. Okay. So with some scaling if required. And I won't go into the details of the swing limits and the biasing. I think you can calculate that yourselves. So basically, this is the cascode op-amp, and this type of op-amp in which you have NMOS diff pair, NMOS cascode, and then over that you have the PMOS current mirror and PMOS cascode stacked. This is called a telescopic cascode op-amp. Probably because the older telescopes had these tubes within tubes which would extend together. I think extend like one after another. It vaguely looks like that, I think. So we saw that in this, the main difference is in the DC gain. Okay. Otherwise, more or less everything is the same. That is GM and consequently the unity gain frequency. Okay. Noise, mismatch. All of these are similar to the simple single stage op-amp. Okay. Of course, you have many more parasitic poles. So you have poles at these are called the cascode nodes A, B, D, and E. The one at C would have been there even in the regular op-amp. Okay. So these are the main differences, and of course, the swing limit is always smaller when you use a cascode device. Okay. So this is expected because you have to accommodate more transistors. And I'll just say you choose VG56, VG56 so that M1, M2 are just in the saturation region, because that's what happens, right? If you lower VG56, nodes A and B, their voltages will reduce, and M1 and M2 get pushed into the triode region. So you choose and of course, if you choose VG56 to be too high, then your lower swing limit will have to go up. Okay, because the output node can come to, what is the lowest it can come to? VG56 minus VT, right? So for swing limit, you have to keep this as low as possible. but you don't want to make it so low that M1 and M2 go into the triode region. Similarly, for swing limit, VG78 has to be as high as possible because the upper limit will be VG78 plus VTP. But you don't want to make it so high that M3 and M4 get pushed into the triode region. Okay. And similarly, same thing for that. Okay. Choose the highest possible VG78, lowest possible VG56, and that is also dependent on your common mode and so on. But the bottom line is the swing of this device is the swing limits of this op-amp, the output swing limits are necessarily reduced. Okay. And even the input swing limits, because on the lower side, of course, the lower limit of VICM is the same as in the conventional case, but you can't go too high because of these transistors. Okay. So, this is okay. Those you can calculate yourselves. Now, of course, there is no reason to choose NMOS common gate device with NMOS differential pair. We could try the other way around and see what happens. Okay. Any questions on the telescopic cascode op-amp? Yeah, I mean, if you find the right combination of threshold voltages and power supply, yeah, I think so. And I mean, maybe a simpler case would be if they're equal, you just tie them together. You only have to generate one bias voltage. Then your swing limit will be VT on either side, VTP and VTN. In practice, with low supply voltages, it turns out you can't use this where you expect any reasonable output swing. But you can use it, for instance, as the first stage of an op-amp, because the output of the op-amp will have, you want to have the largest swing possible. At the first stage output, it will be reduced because of the gain of the second stage. So there you can use it safely. No, that is, if you assume perfect symmetry, they will be the same. In practice, because of mismatch, if you just bias it without DC negative feedback, it will be on the upper saturation or lower saturation. That's the likely solution, right? No, that, see, the output voltage in an op-amp circuit will be decided by the feedback, right? And what input you apply. So it is going to go to that. No, that's what, at DC biasing, so you have the operating point of your circuit, okay? So maybe this is a good time to bring in the, so let's say I'll consider unity gain case, it doesn't have to be. If the input is biased at V bias, ideally, this should also be at V bias, okay? Now what happens is the following. Let's forget random offset. Random offset is because of mismatch. So that will anyway cause a difference between the output voltage and the input voltage. Let's say everything is ideal and the two halves are perfectly symmetrical. Okay. So then if you, let's say we use that same op amp. Now I have this in open loop. It is perfectly symmetric, no mismatch, etc. Okay. What will be the output voltage? I bias both these at V bias. What will be the output voltage? No, not can be. What is it? We have, you must have used this before, right? What will it be? Again, I kept saying something about symmetry and the two halves are the same and so on. Huh? It will be the same as C. Okay, otherwise you get the contradictory solution, right? It's the same as in the single stage op-amp. So this will be VDD minus VSG3 at a current of I0. Okay, whatever VSG3 is. Now, when you place this in feedback, okay, first of all, if V bias happens to be the same as this, right? It need not be, but let's say V bias, I chose it to be the same as that one. What happens when you connect it in feedback? Huh? So basically, all the three voltages are still the same and nothing will change. Now, in reality, of course, V bias can be different from this. So let us say that V bias is VDD minus VSG3 plus some delta V. Okay. So now, how do you get this delta V? How does the output change by delta V? What has to happen? No. You have an amplifier. The output has to change from its operating point by delta V. So what will make it happen? No. That's not, I think you're missing the point. So what I'm saying is that, see, these are all unilateral devices, right? So if the output has to change by delta V compared to the operating point, what should have happened? What is that? The input should have changed by delta V divided by the gain. So the only way this changes by delta V is here you have delta V by A0. Okay. So it turns out this output will not be exactly at V bias, right? So the output will be, you can say approximately at V bias minus delta V by A0, where this delta V is the amount of shift that is required. Okay. It is the difference between the natural operating point and what you want it to be. Okay. So this is called systematic offset. This will be there. That is, if you had the ideal symmetrical op-amp in open loop, the output will be biased at some value. Okay. When you put it in feedback, of course, it should be governed by feedback. Okay. Ideally, of course, there will be a virtual short and you will have whatever you get from the ideal op-amp analysis. In reality, that virtual short will not be perfect because of the finite gain also. There is many reasons for where the virtual short is not perfect. One, of course, is random offset. The other one is the systematic offset, because the output has to change from its operating point to where you want it to go. So roughly, of course, all these are happening together. I mean, I assume that output is V bias and then said the input difference has to be this delta V by A0. But roughly this is okay. If A0 is large, this kind of approximation is fine. Is this clear? So to make the output change from its sort of natural operating point to where you want it to go, the input difference has to be non-zero. Okay, this is just because of finite gain. The higher the gain, the smaller this will be. Okay. Yeah. Right. Not swing limit. Basically, this will be, the swing limit may be affected, but there will be systematic offset. Yeah. But in a two-stage op-amp, see, the swing of the first stage output is small. I mean, the signal won't swing all that much, so it's not as much a concern. Okay. So this is called systematic offset. This is okay. So this will also be there. Of course, if you have a very high gain, this may be negligible. But if you want to avoid this, you should choose the operating point to be the same as that natural operating point, or maybe you should choose that to be the same as what V bias you want to have. Okay. This happens even in the single stage op-amp as well. Okay. Huh? Yeah, it can be negative or positive. Is this okay? So the next thing is you try and use a. So let's say we try to have By the way, just for continuity, everywhere I'll use NMOS differential pair, but of course, you can see PMOS differential pairs used as well. I mean, everything works in the same way with inverted polarity, that's all. So, what is this? This is the NMOS differential pair, and the operating point current is I naught. Okay. If I add an increment, I will have I naught plus delta I and I naught minus delta I. Okay. So that incremental current has to go through a common gate amplifier, right? Now I want that common gate amplifier to be PMOS. Okay. Earlier, what we did was we have the bias current plus the increment, and the entire thing went through the NMOS common gate device. Okay. So the operating point current for the differential pair and for the common gate device was the same. In fact, even that is not strictly necessary. You can make them different if really need to by adding current sources and so on. Okay. But now we have to do that. So let's see. Now we have PMOS common gate devices. We need two of them, one for each. Let me call this I2. So now the operating point current of these transistors M5, M6 is I2. Okay. What I want is to feed these incremental currents into that one. Okay. So how do I get that? I subtract I naught. Okay. What will be the current here? What will be the current there? Delta I, right? I have I naught plus delta I there, so delta I will appear from there. Okay. And similarly, in the other one, it will be minus delta I. Okay. So I feed it to that. Okay. So what is the operating point current in M5, M6? I2. Okay. And what is the incremental current? M5 in this direction. Minus delta I. And here plus delta I. Okay. What do I do next? What did I have there? So this is now my, in place of NMOS differential pair plus NMOS common gate, now I have NMOS differential pair plus PMOS common gate. Okay. What will be the output resistance looking up? It will be GM5 RDS5 times whatever is the resistance of this, plus of course the current sources themselves will also be from MOS transistors, so that will also be there. Okay. Is this clear? So what do I need to complete the op amp? Again, earlier what did I have? PMOS? You are mumbling the most important part. PMOS what? Current mirror. So what do I need here? NMOS current mirror, and it also has to be cascoded, right? Because otherwise you will lose the advantage of high output resistance. We'll see. We'll evaluate. Okay. So now this is a current mirror. So basically here also I'll get I2 minus delta I, and if I terminate this with some terminating voltage, what is the output current? 2 delta I. Okay, exactly the same as before. So the basic operation is the same. So instead of using NMOS differential pair with NMOS cascode, I used NMOS differential pair with PMOS cascode, and instead of using a PMOS current mirror, I am using an NMOS current mirror. That's all. Okay. And this is called a folded cascode op amp. Because current sort of folds its way around the op amp. Okay. Now, of course, you have I0 and I2 in parallel. Basically, that's a current source of I0 plus I2, which has to be implemented using PMOS devices. And of course, it will be biased from some current mirror. Okay. Any questions about the basic topology? So I will remove these lines and then show it. So this is also from some current mirror, and I'll call this M9, M10, and the bias current in this must be I0 plus I2. I0 is whatever bias current you want to have in the first stage transistors, and I2 is whatever bias current you want to have in the second stage transistors. Okay. And of course, this is M3, M4, and M7, M8. They are numbered such that functionally they have the same. They are the same between this and the telescopic cascode op amp. Okay. Is this fine? Now we can evaluate how this op-amp behaves. The primary purpose of using a cascode op-amp was to get higher gain. Okay. So first of all, we can go step by step. What is the transconductance of this? What will be the transconductance of this op-amp? GM1. It's the same as before, right? Because what you can see that the current coming out is 2 delta I, and delta I is nothing but GM times VD by 2. Okay. So the transconductance is the same as the simple single stage op-amp or the telescopic cascode op-amp. Okay. What is the output conductance? Again, we can keep only the dominant terms or output resistance. Either one is fine. The output resistance was a parallel combination of two terms in every case, right? So what is the output resistance looking down? Yeah, it is GM7, RDS7, RDS3, same as before, right? What about looking up? What is the output resistance looking up? Yeah, the important difference is that you have these devices also, M9 and M10. The RDS of that, you can, for this calculation, appears in parallel with RDS of M1. Also, which RDS is likely to be lower, M9 or that of M9 or M1? Which will be the dominant? It is carrying a large current, right? Of course, the RDS depends on length and everything, but still, if you have a larger current, you can expect a smaller RDS. Okay. So that way, these adding this extra bias sources has cost you DC gain. Okay. Okay. And this is likely to be dominant. And of course, the DC gain is a product of the two. DC gain, if you multiply these two, you will get the DC gain. And just by looking at the expressions, you can expect the DC gain to be higher than the simple single stage op-amp, but lower than the telescopic cascode op-amp. Okay. What else will be different between this and the other op-amp, the cascode op-amp? What will be the swing limit? What is the input swing limit? What is the swing limit on VICM? What is the lower limit? What happens if VICM becomes too small? What happens if VICM becomes too small? Which transistor will get in trouble? M0. So it's the same as before. What is the upper limit on VICM? What happens if you go on increasing VICM? So now these two are fixed, right? They are fixed at what is the operating point voltage of those two nodes? What determines the operating point there? It is VG56. Okay. So if you have VG56 here, M5 and M6 will have some VSG. So VG56 plus that VSG will be the operating point over there. So okay. Now the input common mode can go 1 VT above that, right? So on the upper side, it can go maybe even higher than VDD. It is possible because if you choose VG56 to be the highest possible, you will leave just enough room for M9. Okay, you will leave VD sat. This will be at VDD minus VD sat of M9. So then the input can go to VDD minus VD sat 9 plus VT. It can even be higher than the supply voltage. Okay, it is possible. The lower limit is the same as before. It is VD sat 0 at a current of 2 I naught plus VGS 1 at a current of I naught, and the upper limit will be VG56 plus VSG5 at a current of I2 plus the threshold, VTN. Yeah. And if you make this equal to VDD minus, this itself has to be sort of, let me say, less than or equal to VDD minus VD sat 10 at a current of I naught plus I2 VD sat 9. Okay. So this is not very different from earlier. NMOS differential pair, it can go very close to VDD, or in this case even beyond. Okay. Earlier we had a diode connected transistor. Now we have something else. So this can even go beyond that. Okay. One thing you can do is you can just put some typical values for all these op amps and sort of compare side by side what swing limits you get. That you can do by just inspection. Now the main thing is the output swing limit. Okay. What is the lower swing limit? Output voltage. What is the lower swing limit? What happens if the output voltage keeps on falling? Yeah. So what is the lowest it can go to? VG78 minus VTN. Okay. What is the highest? VG56 plus VTP. Okay. Because if you keep on increasing, you can go 1 VT above the PMOS gate voltage. Okay. So the output voltage, the upper limit is VG56 plus VTP, and the lower voltage is VG78 minus VTN. Okay. Now, what about VG56 and VG78 themselves? How would you choose them? How would you choose VG56? Clearly, looking at this, right, this is the output swing limit. How should you choose VG56 to maximize the output swing limit? As high as possible, so that the upper limit is as high as possible. Similarly, VG78 should be as low as possible. Okay. So what should be VG56? How should you choose VG56? Basically, you choose it. What happens? Like when VG56 changes, what happens? This voltage changes, right? If this voltage becomes too high, M9 and M10 will get squeezed. So you choose it as high as possible, meaning you make sure that M9 and M10 are at the edge of triode region, triode saturation boundary. Okay. Similarly, VG78, you make it as low as possible so that M3 and M4 are just at the edge of the saturation region. Okay. So, VG56 itself should be less than VDD minus VD-SAT9 at a current of I0 plus I2 minus VSG5 at a current of I2. Similarly, VG78 must be greater than or equal to VD-SAT7 at a current of I2 plus VD-SAT3 at a current of I2 plus VGS5 at a current of I2. Okay. Right. VGS7. Okay. It's easier to look at the picture and imagine what is happening. So, if you keep on lowering VG78, but without letting any transistor go into the triode region, M3 and M4 will be at the edge of this triode region or saturation region. So, then you have to leave one VD-SAT for M4 and one VD-SAT for M8. That is the lowest limit. Okay. And similarly on the upper side. If you do that, you will get V0 to be basically the upper limit will be and here okay. That's what it will be. So, one big difference between this and the other op amps is the swing limit. Okay. You just have two transistors on the top and two transistors on the bottom. It's also sort of symmetrical, right? Whereas the others were skewed to one side, this one is symmetric. Okay. So, this is the primary advantage of the folded cascode. Okay. Any questions about these? Swing limit. Yeah. So, the input swing limit is also slightly higher on the higher side, and the output swing limit is definitely better than the telescopic cascode. Okay. Parasitic poles. We will see. Yeah. So, we will look at all those things. So, again, I think I call these nodes A, B, C, D, and E, right? Those are the additional nodes besides the output node, right? And there will be parasitic capacitances everywhere. That part is the same as the telescopic cascode. In fact, C was there even in the simple single stage op amp. So, what is the primary difference between the telescopic cascode and this as far as parasitics are concerned? At A and B, the parasitic capacitances will be larger because earlier you had only two transistors connected. now you have 3, and in particular M9 and M10 will also be larger because they are carrying higher currents. Okay, so those parasitic poles will be at a lower frequency. You have the same number or the same phenomenon, but the parasitic poles, 2 of them are likely to be at a lower frequency than before. Okay. What about noise and mismatch? What about noise and mismatch? More. Why? So everything else remains the same as before. What did we do for noise and mismatch? We connected current sources across each of the devices, right? And saw how much comes to the output. The rest of it remains exactly the same. Okay. The ones from M1 and M2 appear fully. Ones from M3 and M4 will appear fully. M5 to M8 will not appear at all. I mean, at least if you assume that GDS is 0. Okay. And again, one from M0 also does not appear because of symmetry and cancellation. But you do have M9 and M10. Okay. So if you do have current sources from there, let me remove some of this stuff. Okay. So now you have these current sources IN9 and IN10. What happens? What will be, let's say IN10, where does it go? What happens to IN10? Where does it flow? So basically that will go through that to the output, and this also it will get mirrored and go through like that. So this will be IN10, this will be IN9. So you also like before, you get the sum of currents from M1 to M1, M2, M3, M4, also M9 and M10. Okay. So the output noise current or the output current because of these additional currents will be IN1 minus IN2 minus IN3 plus IN4. Some of these could be flipped, but have okay. So now basically this adds both to noise and mismatch. Okay. And again, remember M9 and M10 are larger transistors. They have more current. They are likely to have more GM. So that means that the noise current will be higher. Okay. Because the noise current of a MOS transistor is just proportional to, the noise current power spectral density is proportional to GM. And the same goes for mismatch. Okay. So in that way also, this folded cascode is worse because this you need these additional biasing sources, to bias the cascodes, and they will contribute to output conductance, noise, and mismatch. Okay. So what was the, again, I won't go through the derivation, but what was the expression for the noise current output noise current spectral density? What was it? 16 by 3, 80, GM1 plus GM3. Now we will also have plus GM9. Okay. And of course, the input referred noise will be the whole thing divided by GM1 square. So, okay. So, this is from M9 and 10, which are used for cascode biasing. Okay. What do you mean? No, it is after M9, M10. I don't know. No, the input current has to pass through the common gate amplifier. The current in the input differential pair has to pass through the common gate amplifier. Okay. So, similarly, what will be the expression for the offset variance? That is the input referred offset. What was the earlier expression? What is it now? What is the first term that you will always see? Due to M1 and M2, you will see sigma VT1 square, okay, plus what did we have? Sigma beta 1 square times I naught by GM1 square, okay. So, that part we will still see. And what else? What else did we have? Sigma VT3 square times GM3 by GM1 square plus sigma beta 3 square times, in this case, it is I2 by GM1 square, okay. Plus you have the contributions from the additional biasing devices. What will that be? It will be sigma VT 9 square times what? GM9 by GM1 square plus what do you have? Sigma beta 9 square times I2 plus I naught by GM1 square, okay. Now again, because these transistors are bigger and carry more current, GM9 is likely to be larger than GM1. So, this contribution will be quite significant, and so will this, okay. So, you have extra noise and mismatch because of the cascode biasing devices, okay. So, the main advantage is the swing. Other things are similar or worse in that the output conductance is higher, the noise and offset are also higher, okay, and the parasitic poles, two of them will be lower because you have more devices connected there and the devices are larger, okay. So, if your only thing is, if you want some appreciable swing, especially with low supply voltages, you may have to use this. So, now you also know the trade-offs, okay. So, please calculate the noise and mismatch and the small signal picture of at least the single stage, simple single stage op amp and the cascode. After that, I think if you see a new topology, you will be able to do it yourself, okay. Now, since we have come to the folded cascode op amp, right, this leads to another interesting, I mean, it's not a great op amp, you use it only in like desperate situations, but sometimes useful nonetheless. analyze this structure, I have too much clutter here. First, let me get rid of this. In fact, some part of it you have already done. Just imagine that the bias current is I2 through this, right? Through this whole thing. And then I have incremental currents, let's say delta IA and delta IA that way. This you already analyzed. This is what happens in the folded cascode. And let's say we have you inject it to the sources of M7 and M8, the other cascode nodes, okay, and find I out as a result of this. We'll continue the discussion from there. This needs some inspection, analysis by inspection. Just do that and see. Okay. Any questions about the folded cascode op amp? Okay then, see you all.